we know what's going on. We're going to play chase. So player is blue, red box is the computer. Move far enough away it can't see or smell you anymore. If you get close, if you're feeling bold, then it starts to chase you. Setting something up like this, we'll learn, requires thinking about a few things, such as relative speeds. If the enemy and the player are moving at the same speed, it gets hard to run away from it. If the enemy is moving faster than you, it's impossible to run away from it unless you have things that you can hide behind, or if you can do asteroid screen wrapping and perhaps sucker it over to one side, you go to the other side, and now you're far enough away. When the collision occurs, the screen does turn yellow. So that's what we're going to work on making this afternoon. So when we look at the move file, which is where move start is where we're going to begin, because that's the file that we're going to add all of our content to this afternoon. So in move start, right now if I run this file, it doesn't do anything. I press the keys, nothing happens. Now, the way that we're able to work with our key input is we use the key pressed and key released functions. So those are functions that listen for the events that have happened. So every time you press or release a key, the program is aware of it. That's how these kinds of things work. Is you press a key, it goes, hey, a key is pressed. You release a key, hey, a key is released. And then the program's smart enough that we can ask it, we can say, hey, can you tell me if it was a specific key? And it will say yes or no. Well, we have these cool little booleans up here, left, right, up, and down, which are going to correspond with the values, the yes and no values that we are going to be working with here. So we are going to then write a little bit of logic into our key pressed and key released that's going to enable us to then set those values. So when I press a key, say I press the left arrow key, then I want my Boolean value of left to switch from being false to true. When I release the left arrow key, I want it to go back to being false. So that means we need to now populate these two functions, these key pressed functions. In populating these, we have two ways that we can go about doing this. We can do it where we write if statements, but it's also possible to write it using what is called a switch statement. And a switch statement is a little more condensed way of writing. If, else if, else if, else if, else if, else if kind of statement. A switch statement just is a lot cleaner and easier to read. So I'm going to write it with the if, else if first, so we can see what that looks like, and then rewrite it using the switch so we can see that. And in this type of situation, switch is usually going to be a preferred way of doing it. So if we start out, so I'm going to recommend that you skip the if else if and just wait for the switch before you add any code to your own, but it will be useful to see the difference. So what we can say is when we've pressed a key, we can ask the question if the key code, and every key on your keyboard is associated with a key code or a number. So we can now track all the letter keys, the space key, the return key, the enter key, the number keys, the arrow keys, the shift key. All of these have specific numbers. They're ASCII character codes or key codes that are associated with it. And if you don't know what they are, you can just ASCII key codes. And when we do that, we can go find any of these kinds of things. Will tell us what those numbers are that are associated with it. So that if I look through on my list here, we can see the letters and what key codes are associated with them. I don't like that chart. That's not a very pretty one. The Adobe one's easier to read. So the key code for the letter A is 65. We can see the key code for lowercase a is 65. The character code, 97 and 65, now are different. So we have character codes and key codes that go along with it. If we just grab the key code, so if we look through, there's function keys, arrow keys. left arrow key has a number associated with it of 37. The up arrow is 38, the right arrow is 39, the down arrow is 40. So the 4 arrow keys on your keyboard are going to correspond to the numbers 37, 38, 39, and 40. So that will become important as we then write our conditional to check for it. So right now we're going to be working with the arrow keys of the 37, 38, 39, and 40. Spacebar is 32, shift is 16. Those are other common keys that you may work with. And then we can also, if you wanted to program game interaction using the letter keys, so instead of the arrow keys, but letter keys in the keyboard, you just go find the corresponding character code or key code that goes with it. So if you wanted it to be WASD, which is another common 4-character combination for, say, on-screen movement for a lot of computer games. So then we can see A is 65, W is going to be 87, D is going to be 68, and S would be 83. So you can go find your codes that way. So if my key code is, and the first number is most common, you just kind of work your way around the clock, starting with the left arrow at 37, then up is 38, right is 39, down is 40. So it's like going around the clock at that point. So if the key code is 37, just put a comment, left. And well, I don't really need a comment because my next line of code will be left is equal to true. Don't really need, that's kind of obvious there. All right. And then I need my closing curly. Now I can say else, and this is where I'm feeling a little bit lazy. So we need 4 of these and get rid of the final else. So if it's 37, the next one is going to be 38, the next one is going to be 39, the next one will be 40, and then it's left, up, right, and down. So when we look at this, this is a perfectly functional bit of code, and this sets those values. Now our sprite is eventually under update. It's going to say, hey, if left is true, then start moving to the left. If right is true, start moving to the right. Up, down, respectively. So it's going to worry about that in its update in a little bit. I mean, we can even just put that in. If left speed x is equal to -2 x plus equals speed x. So if I press the left key right now, theoretically, my player, it showed up on screen. So up key, right key, down key, left. Oh, it works, but now it went off screen. So that's problematic because now I need something like else if not left, which that's the same as saying left is equal to false. Speed x is equal to 0. Now I have no way, once I make left become true, do I have any way to make it go false? No. But we can very easily, and we will switch this over to the switch statement in a moment, just because if I just have the 4 numbers, it's okay, but typically if we're building something, we're going to have the 4 numbers, plus we may have a few other keys for additional functionality. Say I want my player to be able to shoot at things. I want it to be able to jump. I want it to be able to do other things, activate a shield. All of these other things are more keys. As I get more and more keys in the list, using the if-else-if just becomes a very ugly looking way of working, and it's much easier to go about using a switch statement. So now I have a way to make left become false. So if I release a key and the key code of the key released was 37, then it will make it go false. So now if we run this, we'll see, and now it stops. Now none of the other keys work yet, but it's a start. It's baby steps. We're trying to do baby steps to get the whole thing going. So that's using our if statements. It's not terribly pretty. What I think looks better is we use the word switch, and then we specify what are we switching on, and it will be on key code. And then we throw our couple curly braces in and then go back up. And then what we do is switch will specify specific cases. So when the case is 37, left equals true. Now we have to put the word break in here. Well, I'll explain that in just a moment. Case 38, right is equal to true, break. Case 39, oh, it's not right. Up. Case 39, now it's right is equal to true. Break. Case 40. So we do case 40 and then a colon. We have to remember the colon. So there's a different kind of punctuation when using a switch, but I really think it's easier to read. Yeah, we're going to skip the default today. All right. If we look, we have a whole bunch of curly braces using the if-else-if method. With switch, we end up with this really nice, organized, much cleaner indents, easier to read type of code. This is typically much easier to troubleshoot than the ifs with all their curly braces and extra parentheses. Doing the switch statement is a lot easier to troubleshoot. With the switch statement done, I'm going to ditch the if-else just for easier to work with. Now, one thing about switch statements, it's common if you forget to put the breaks in, what ends up happening is the switch statement reads, it checks against 37. And if 37 is true, but break isn't here, so if I were to comment it out, it's going to go down to 38. And then check on that one, and then do 38's behavior because it goes until it hits a break. So once it's true, it just moves down to the next case. What break says is, oh, if it is 37 and that was the key that was pressed, stop checking. That's how that works. It says stop checking, get out of here, get out of this set of curly braces. So break says exit whatever kind of loop that you're running through right now. So now I'm going to use the same switch statement inside my key released as well, but change all of my trues to false. So now I have my 37 is left, 38 is up, 39 is right, 40 is down. And then we have 4 trues, 4 falses. So my key pressed and key released methods or functions are done. I don't have to do a thing to them ever again. They're done. I don't have to rewrite them. I can move them from project to project with no issues provided I set up my 4 Boolean values of left, right, up, and down. So it's one of those, once you have this, you typically just copy paste these chunks of code from a project to a project, or make a separate file that you just dump, so you could make a little file that has some of this information and just move it from folder to folder as a separate PDE file, and that would allow it to work as well. But that now makes it work. So now the only thing is to worry about how to make our sprite start behaving a little bit with its movement so that it figures out what to do. And that's where it gets fun. The next round of updates are going to be inside our sprite here, that we are going to add in some movement capacity for Mr. Sprite. But we're going to do it a little bit different. So I'm just going to get rid of that right now. So when we do this, what works well is we first start out and we get the sprite behaving, moving just on the x-axis. Then we worry about getting the sprite moving on the y-axis. But we don't try and deal with both at the same time. So if I press left, I want speed x to become a negative value. If I press right, I want speed x to become a positive value. Now, I'm not going to worry about killing the speed and actually, we'll just get rid of all of that. I don't want that for now. So right now, I can make them go back and forth. So currently, left and right start out as false. Once I press a key, it's going to start moving. So I'll be able to keep them on screen just by moving right, moving left, moving right. But I can't make them stop. I have no way to make it stop. So now that's the next component, is how do we force him to stop? And the situation in which we want speed x to be 0 is when both left and right are not being pressed. Because what I had there before would work for left, but then right would get all messed up with it. But if left is false and right is false, now that the exclamation mark in front of the word is the same as saying not. That is the programmer code for saying the word not. So if not left, well, left has true and false values. So if I say if left, that's the same as saying if left is true. If I say not left, that's the same as saying left equal to false, or asking that question, is left equal to false? So that's why we use not. Now that, if that is too kind of cryptic when you look at it this way, you could write your statement as if left is equal. So ask the question if left is equal to false and right is equal to false. So these two lines of code are performing the identical action. They are making the same thing happen. Now, if you look through most references on code in programming books, they are going to use the exclamation mark to signify not. So you can decide how you want to go about doing it. If you use the second version because that makes more sense to you when you read the code, go nuts, that's fine. But I want you to be aware of the other form, because if you come across other people's code, books on code, they're going to more often than not use the exclamation notation, which is the same as saying, asking that question, is left equal to false? or is right equal to false. And is right equal to false, not or. That's an and. The 2 ampersands is and. But I am going to use that notation. So if you want to make yours where you say left double equal sign false and 2 ampersands, right double equal sign false, that's totally fine. And now I can say speed x is equal to 0. Now if I run my project here, if I hold the button, let go, stops. Hold the button, let go, stops. So now we can see it's working. The only other situation that it's not a requirement to take care of, is what happens when I'm pressing both at the same time. If I'm pressing both keys, do we want it to keep moving? Do we want to kill the movement? And that's up to you. You can do whatever you want on that. And the way that we would do that is say else if left and right so if left and right are both false, or if left and right are both true. And the way that works is when I'm pressing both keys, I don't get the little kind of jittery movement. It just kills it, meaning there's too much input. So now I have to be deliberate and be only one key or the other. Now, this gets it moving left and right. Moving up and down should be a straightforward adaptation of this, where you just simply change x's to y's and left to up and right to down. And then you can now make your player or your sprite move in all directions. So it becomes just a matter of replacing left with up, down, right with down, speed x with speed y. Everything else stays the same. And then we just need one more line of code similar to that, where it's now y plus equals speed y plus equals speed y. And then run your project, and we can move down, we can move up, we can move over, and we can even move diagonal. The sprite has been created. The sprite is now responsive to the input from the player in our limited movement vocabulary. Our next order of operation is to then create our enemy. The cool part about the enemy is essentially a variation of the sprite class, except that its update is going to be a little bit different, because instead of responding to the keyboard inputs, it's going to have to become aware of where's the sprite on screen so that it can now chase it down. And then its display will be updated with something so that we can tell that it is indeed a different element. And then once we get the enemy chasing it down, then we'll figure out how to determine when the two have overlapped or a collision has occurred. Now the cool part about building our next object is we can just make a second class by copy pasting the sprite class and changing the particulars of it to make it happen. Now you can, if you want to be working in separate tabs, you can be in separate tabs, or you can be in a single tab. It's up to you as to how you want to go about doing this. I think now that this is getting long enough, I'm going to break things into a separate tab. So I'm going to cut that out of there. So I highlighted all of the content that was my sprite. I will say new tab. Call this sprite, the capital S. Paste it in. There's my sprite. Now our enemy is going to be very much like the sprite class. So as long as we currently have this on the clipboard, we can repeat this process and say new tab and call this enemy, E-N-E-M-Y, with a capital E. Hit OK. Paste. And then we will change the class name to enemy. Change the constructor to enemy. And now we have an enemy. Now the enemy's update information is not going to be any of what's currently there, except the x, plus and equals speed x and speed y. Its display, we will want to change the color of it so we can tell that it is indeed our enemy. Actually, I'm going to go with green. And then when they overlap, we can make red. So you can choose display however you want. I'm going to make the enemy bigger. Because then when it's bigger, we'll be able to see it on screen. But it also would make sense for the enemy not to spawn where the player is spawning. Because currently sprite spawns at 100, 100, and now the enemy would be spawning at 100, 100. So probably not a good idea. So we can change that. Now you could have the enemy spawn in a fixed location and the player spawn in a fixed location because then they're racing to something away from something or whatever it is. Or we can spawn it into a random location. And I'm going to just say it's going to be a random location somewhere between 100 and the width of our screen minus 100 is where it's going to appear. And do the same thing for height. So now the enemy will spawn somewhere on screen. It might spawn where the player is. Now, if we want to guarantee they don't ever start the game on top of each other, we could modify this randomness. So instead of 100 for our minimum, let's see how big was my whole movie is 800 wide. So I could say it always is going to start somewhere on the right side of the screen. So we say from 400 over. So it's never going to be starting right next to the player. Well, that works. So now we have an enemy class. Doesn't do much yet because it has no speed. It's not going to move. We'll figure out how it moves in a little bit. And then if we go back to our main file, in this case it's move start. This is where now we add an enemy. And I'm going to call mine E. You will notice that I'm trying to show economy of keystrokes here. The fewer keys you type in, the fewer typos you can make. So as long as what you're typing makes sense, you're in good shape. So we create our variable E, which is of type enemy, then say E is equal to a new enemy and our setup, and then inside our draw we just simply tell E to update and E to display. Now if I run this, we'll see that there it is. Popped up. Now it's not doing anything yet, but you can see that it's working. When I want the enemy to chase the sprite, there's many different ways that we could go about doing this. What we want to do is figure out where is the sprite in relation to the enemy so that the enemy will move towards that object. Now, there's two common kind of ways of going about doing this, which is when we look in this situation, if we look at these two objects, we'll see that they're further apart on the x-axis than on the y-axis right now. So we have an option, which axis do we want to close first? Do we want to narrow up the short distance and then narrow up the long distance, or narrow the long distance and then finish with the short distance? Both are correct. They each have a different visual impact when it's done, and you get to figure out what makes the most sense for you. So what we have to do is figure out which distance is greater, our distance apart on x or distance apart on y, and then work to close that gap. And then once we close one of the gaps, then we try and close the other one. So that's the process that we're going to go through here. So we're going to figure out, do we want to move horizontal first or vertical? Close the small gap first. So if I move like this, now the small gap has been closed, and then it will do the big gap. Of course, the green object will move to the blue object instead of the blue one moving to the green. But that's what we have to figure out. So the first step in this process is to ask the question, which is greater, the distance apart on x or distance apart on y? Now our enemy, as we look at it right now, it knows its own x and y, but it has no idea what the x and y is of the sprite. So we need to send it that information. So we did some of the sending on the solar system. We did some of the sending on the catcher game, which is inside our main class, move start. When we tell the enemy to update, we just need to tell it about S. And now we will get an error message right now because currently it's not expecting to learn about S. So if we just put S in there, on our e.update parenthesis S close parenthesis, then inside the enemy, in its update, we go sprite S. So that means we've now passed in it. Now if I go back here, we see the error message went away. So what we're doing is when we tell the enemy to update, we're sending it knowledge of that S object. So we're telling it, hey, I want you to know about S. And it'll say, cool, thanks. Because now that I know about S, I can ask the question. I'm just going to write a comment so I can write it in plain language. Then we'll figure out how to put it into code where I can say, is our distance apart on X smaller than Y, or vice versa? So that's what we have to figure out. So to try and determine that distance, what we can do is we can now subtract the location of one object from the location of the other. And then we can find out what is that distance between these two objects. Now, we also could use our distance function, but the distance function is just telling us between 2 points, not just between x or between y. We will use distance in a little while later because then when we set a radius of awareness, so we want our enemy to only be aware of the player when it's within a certain distance away. And we'll deal with that in a little bit. But right now if we say if, and what we have to do is find out what is the actual distance between two values. And we're going to use our app workout here, which I'll explain in just a minute. And we take the x of our enemy and subtract from it the sprite's x. And we're going to find out, is that greater? No, less, sorry. You guys decided less. Y minus sprite's y. So what absolute value does is that says if I subtract two numbers, if there happens to be a negative value, like -3, -5, it gets rid of the minus. So if I take 3, or if I take -3, if I say what is the absolute value of either of those, the answer is 3. So the absolute value of a negative number is just the number itself. We get rid of that minus sign. So if and this matters because oh, I forgot a parenthesis here. Let's try again. This matters because right now the player, if we ask this question, if the absolute value of the x here minus the x of the box, well, this x is bigger than this x, so I'll get a positive number. But now, if the player is over here, the player is a bigger number. Let's just say, for instance, this is 750 and this is 700. Well, 700 minus 750, that's -50. But I want to know what is the distance apart. I don't care whether it's -50 or +50. I want to know how far apart these two objects are. So absolute value allows me to just say, what is the distance between these two numbers? Not if I take a number, subtract a number from it, and I get a negative. I don't care if it's negative. I just want to know what is the number. And that's what absolute will return to me. So now if this is the case, then it's going to be close the horizontal gap. And our other situation would be else close vertical gap. So these are our two situations because we're either going to be closing the horizontal gap or closing the vertical gap. The next order of operation is to figure out, well, in which direction do we need to move to close that gap? And that's what we have to figure out next. Staring at the screen's not going to work. Watching it take place does make more sense. So, horizontal gap, what I need to do is figure out on what side. So I'm going to use an if. So I'm going to ask, if the x of my enemy is less than the sprite's x, so if the x of the enemy is less than my sprite's x, I need to go right. Now I'm going to just pull it back up. I had to finish typing something. So if the x of the enemy is less than the sprite's x, that means the enemy needs to move to the right. Oh, I'll just leave this up here so I don't have to, so we can see it. So to go right, then we just have speed x is equal to 2. Now that makes the player have the same speed as the enemy. So I'm going to have to modify my, well, I'll just make this 1 so I don't have to go in and change my sprite speeds. Because if I give them the same speeds, we're going to have a broken game very quickly. But 1 and 2 for our speeds is kind of painful. Usually I give players a speed of about 5, and I give enemies a speed of about 2 or 3. That seems to be a more manageable number. But when we're trying to figure out collisions and intersects and other stuff like that, it's better when things move slower. So that's why I'm using some of these small numbers. Now, if we're not going right, that would mean we are going left. So to go left, speed x is equal to -1. So closing the horizontal gap, if we're trying to close the horizontal gap, that's going to work. Now what we can do is, let's rerun it and see what we have here. So we can see now it's trying to close that gap until I get far enough out, but I don't have any way to set the speed back to 0 yet. So once it's moving, and now if you look real close, we can see that the enemy is almost quivering. It's got a little bit of the shakes going on. And if our speed was greater than 1, we probably would see the shakes going on. So that gave me my closing my horizontal gap. Closing my vertical gap is going to be the same sort of thing. I just will do it with y's now. So if the y of the enemy is less than the y of the sprite or the player, that means we need to make it go down. Going down would be speed y is equal to 1. Then else, don't forget a curly brace. Now else, speed y is equal to -1. So we either close the horizontal gap or we close the vertical gap as part of this. But once our program is running, we will see that it's closing the one gap. Now it wants to close. But it's always going to be trying to chase me around on the screen. One thing that becomes noticeable when it's running is when it gets onto the line, we see where it gets a little bit twitchy when it starts to get aligned with the player. And you start getting some weird twitchy. And it also now, at a certain point, once it crosses the line, it can run into situations where it just keeps going because it's closed one gap, and now as it tries to close the other, it thinks it's done, but because when the gaps are too small, it gets confused. So what works well is if we're moving on one axis, we kill speed on the other. So if we're moving on X, then we kill our speed Y. And if we're moving on Y, we kill our speed X. Or to use a nonviolent metaphor, we set our speed X or speed Y equal to 0. So apparently, if we want to cut it or modify it so that it closes the small gap first, it ends up getting into some weird behaviors. But if we close the big gap first, I wonder though if we just, one more thing to check on this. All right. So what apparently needs to happen with this is we need to, whatever distance is greater, we need to close that gap first, and that makes it behave better. So previously we had a less than sign on our first if. If we change that to a greater than sign, and then, so if the horizontal separation is greater than the vertical separation, then we close the horizontal separation, then we close the vertical separation. So I'll have to think through the math a little bit more to figure out why it was misbehaving. But now with that, it wants to close. So when you get kind of out at a 45, it comes in at a 45. And now we can make it chase. Now there's some other ways that we can go about this where we can say once it's moving in a particular direction, it keeps moving until it has completely closed one of those gaps, and then it reevaluates to determine its new direction of movement. But that type of, that just requires more conditionals, more checks, and more things to keep track of. And the goal right now is just to keep it simple. Our next operation, when we start building things chasing, we will probably look at adding in with some trigonometry so it's moving on an angle. So we rotate to move on an angle, because then that makes it super easy, because we just say point in that direction. So if they're chasing the player, we just point to the player and then move at whatever their allowed speed is that it moves. And then that works out really slick. Enemy chasing, the other option would be to add into it where we set up a radius of awareness. So we say, ask the enemy, don't start chasing until the player is within so many pixels of you. So we can do that by comparing the distance between 2 points. We compare it between the point of where's the player and where's the enemy. And we look at those 2 points, and if that distance is less than whatever our threshold number is, then it will start to play chase. So to do that, so we find the distance between enemy and sprite. Oh, not bar, wrong language. So we'll call that, I'll call it distance apart is equal to, and we use our nice handy dandy equation built into. This is essentially the quadratic equation. We plug in 2 points, and then we say, what is the hypotenuse of this triangle? But we do x, comma, y, comma, the sprite's x, comma, and the sprite's y. So we say, what is the distance apart? And then we can say, if distance apart is less than, I'm just going to throw out a round number like 300 right now, then we do curly brace. So if the distance apart is less than 300, then we want some chase action to go on. So all of that. So we go all the way down to right before the x plus equals speed x and y plus equals speed y. And then we will put in a closing curly brace. And then say else. Put another curly brace, and then speed. Because if we're not chasing, we want the speed x and our speed y to be equal to 0. And a final closing curly. Now, if you've put all your curly braces in correct, if you click on your final close by your final closing curly, we'll see it lines up there. Click on the one by the else, it goes up to by the distance apart. It's always a good idea to click on curlies and see where the program thinks its matching pair is. Once you get all of that set up, Command T or Edit Auto Format, that will clean up your indents, and then you'll see how nice and pretty everything is when it indents itself on screen. So we get a nice set of indents going on. So we can say if the distance apart is less than 300, so that means they're somewhat close, then we start making it chase. Now when we hit run, we can see now it's not chasing. It's not chasing. And now when I start cutting that, oh, move away. And because I'm so slow, it's hard to get away from it. But if I persevere, I can do it. I get close. Oh, it's chasing me again. That's bad. That's bad. That's very bad. Because it's probably an infected zombie, and if it touches me, I'll be infected, and it'll just be like Walking Dead all over again, and we don't want that. To talk about rectangular intersection between objects. When we have objects on screen, whether they're a rectangle, square, circle, doesn't really matter. Right now we are going to do box-style collision. We did circle intersection on the catcher game. Now we're doing box-style intersection. Now with box-style intersection, it works a little bit different. What we know is we know the x and y coordinate of our object. We also then know how wide and how tall that object is. So we have that data to work with. Now if we look at these two objects, we can see if we compare between these objects, they are not overlapping on the x-axis. But we can see they're overlapping on the y-axis right now. And when we're doing box-style collision, what we do is we first say, are we overlapping on one axis? And if we're not, then we're not intersecting. I mean, there's no possible way the objects are intersecting if they're not crossing on at least one axis. Now, if we go here, the objects are overlapping, but we can see on the x-axis, they're overlapping right there. And on the y-axis, they're overlapping. But now if they're overlapping on the x-axis, but not on the y-axis, they're not overlapping each other. So it's trying to figure out how to write an algorithm to deal with that we're going to work with. And the way that we end up doing it is we try and figure out from the object's midpoints, from this midpoint, I have half of the object. And from the object's midpoint, I have this other half here. Now, if those two half widths, this square and this square, these two half widths, if those two half widths, the distance between the middle of this object and the middle of this object, right here, so the distance, oh, wrong tool. There we go. So the distance between the middle and the middle, if we look at that, and now we'll put this object back in just a moment. I need to draw one more line. Now if we look at a line, here's a line that represents, this is the sum of half of this object, half of this object. That's what this line represents. So these two objects right now, if I look at this line, we can see, well, this is the sum of half of yellow, half of blue. This is the distance apart from their middles. Well, they're clearly not overlapping, but this line is clearly bigger. But when they're overlapping, this same line is now shorter. So we can see they are indeed overlapping. So what we compare is we're comparing midpoints to the sum of their half widths. So we take the half width of object A, half width of object B, add those together. That's this line right here. We'll give it a, make that red so it's easy to, so that's our red line. Now the black line represents what is the distance apart those two objects are. So if they're here, this black line, now if we compare it, we can see the black line is bigger and they're clearly not overlapping. So what we're going to be looking at is from the middle of the object to the middle of the object, how far apart are they, versus what is their half width size. And then everything that I just talked about on width, we will also do for height as well. So we compare half widths to distance from middle point of the objects. That's how the algorithm works. The other option is you copy the algorithm in, you save the file, and you go back to it in subsequent semesters. Now, what I find is some semesters I challenge myself and I don't reference an old file and I go back and recreate it. Other semesters I'm on a time crunch or just feeling lazy that day, and I go open up an old file and copy paste it in and say, hey, look, I got it, I'm so smart. It is what it is. You figure it out. But it's half widths versus distance from the middle of the objects. That's how we're going to find out if they're intersecting. So to do that, the same way that in our catcher game we had an intersect function inside our main file, we're going to do an intersect function in our main file here. But instead of calling it intersect, I'm going to call it rectangle intersect. Now, rectangle intersect is going to be accepting my sprite. I'm going to call that R1. And my enemy, I'll call that R2. The same way that when we did the catcher game, our intersect function, it took catcher and ball. Now we're feeding it sprite and enemy. And I spelled enemy wrong, so that would have been really frustrating down the road. There's only 2 E's, not 3 E's in enemy. So once I know this, what I need to do is I need to figure out what is the distance part on X axis. Then I will need to, what is the distance part on the Y axis. Then what is the combined half widths, and what is the combined half heights. And my typing skills are abysmal right now. So once we determine those 4 values, then we check for and sorry, this isn't a void, my bad. It's not going to be a void. Intersect in our catcher game was a Boolean because it returned a value. We asked the question. Right now I'm just going to put a return false, because if we make a function that is not of type void but it returns a Boolean, we will keep getting an error message until we at least tell the program that it's returning something. So our comments here are what this function is now going to have to do. It's going to have to calculate the distance on X, calculate the distance on Y, calculate my combined half widths. So I take the 2 half widths, add them together, calculate my combined half heights, take the 2 half heights, add them together. And then it does a comparison on distance to say, hey, is my distance less than my widths? Okay, then is my distance on Y less than my heights? And if so, boom, we're intersecting. Otherwise, we're not. So it's going to return either we intersected or we didn't, just like the catcher game's intersect function did. So to determine distance apart on our x-axis, I'll just call it, it will be a float, we'll call it distance x. And what we are going to do is we will grab rectangle 1's x plus half of its width. Now, looking back in Illustrator here, we'll go back to the code in just a moment. Remembering that our objects measure their coordinate system from their top left corner. Well, I want to go from the middle because I'm trying to figure out what is, the distance between this midpoint here and this midpoint here. And that distance is x plus my half width. And this is x plus my half width. So that means we add that. And then we now subtract from it rectangle 2's x plus its half width. So that's rectangle 1's x. I probably should put spaces in there, made it look a little bit prettier. So rectangle 1's x plus half of its width, rectangle 2's x plus half of rectangle 2's width. So that now gives me my distance x. And then we repeat the same thing for our y's with heights. So we take rectangle 1's y, add to it half of its height, subtract rectangle 2's y plus half of its height. And one thing that you may notice is that it's possible distance x and distance y will return a negative value. But the reason that we're leaving it in that right now is later on, if we get a positive or negative value on distance x and distance y when we're trying to figure out intersection, we can then find out on what side did the objects intersect. So we can find out, did we have a left side hit a right side or a top side hit a bottom side? So by not kind of removing the positive or negative from this, then we can take advantage of that knowledge down the road. So we will have to do absolute in a little bit, but not yet. Oh, my comment's in the wrong spot here. My comment should be up here. So we distance apart on the x-axis, distance apart on the y-axis. Now I need to come up with some combined half widths. And that would be, my combined half width is going to be equal to R1 and its width divided by 2 plus R2's width divided by 2. And our combined half height will be equal to R1 dot h divided by 2 plus R2 dot h divided by 2. So once I have these four numbers, then I can find out, has an intersection occurred? And if an intersection has occurred, at that point I can do something. I can make something happen. I can blow up the world or whatever take a life away. Make the sun shine. Have pretty clouds in the sky. Whatever works for you. Have our different variables. Now it's time to put them into action. So the way that we do this is we just say if the absolute value of our distance x, so absolute parenthesis distance x close parenthesis, is less than, so if the distance apart is less than my combined half widths, that means they're intersecting on the x-axis. So once I know that, now I need to check for intersection on y-axis. So I do a second if ABS parenthesis distance y close parenthesis is less than my combined half height value, huzzah, they are intersecting. And then return true, close parenthesis. And I think so the final part on our intersect is we check to find out if the intersection happened. Check for intersection. I should just complete this on x-axis. So we check if the distance is less than the combined widths. Then we check on the y-axis. If the distance is less than the combined heights, then huzzah, they're intersecting, and we return a true value. Once we say return, we effectively exit this function. But if we don't return a true value, meaning they didn't intersect, then it returns, the function itself returns false. That's how it works. Now, if it bothers you having the return true here, and you want return false to be inside some curly braces, it's either we intersected on the x-axis, but if we didn't, we could just be else. So either we intersected, but then we would have to have another return false, and yeah, I don't like that. Oh. So it really is cleaner when we're doing a return function where it returns a Boolean value. As a matter of course, you typically will just put return false at the very end, and somewhere else in the function, it returns true. So if it can return true, it does return true. If we go back and look at our catcher game, its intersect had the return true, else return false. So it had it wrapped in an if statement. But based on how this one's working, we don't really need to do it that way. And this is a cleaner, it requires less curly braces. Anytime we can get away from nesting more and more things where you get curly braces 18 layers deep, I'm a big fan, because too many curly braces makes it really hard to figure out what's going on. So when we have this happening, then to use it, we say if rectangle intersect, and we pass to it our objects, and then we do something. Now in this case I'm doing a red overlay, but you could also subtract a health value. Then you could check a health value and find out if the health value has gone into negative numbers. You could change game state, or you could do something else, or you have the skills now. You program the catcher game, you can apply that same knowledge to this.